Okay, in this video we're going to continue kind of messing around with vectors and vector spaces. And in particular in this one, we're going to look at bases, as in plural of a basis, where we understand what a basis is now. Say we have the standard basis for R2, R3, for a bunch of other vector spaces. But we also understand that, say, for R2, as long as I pick two vectors in R2 that are linearly independent, that will form a basis in R2. And the question then becomes, well, is there a way maybe to take something written in terms of one basis and write it in terms of another basis? We're going to look at a geometric understanding of that up to my ability to draw it at least briefly. But before we do that, just to kind of reiterate something that we mentioned in one of the previous videos to kind of see where we're going with this. We said if B is a basis for V, then every vector X can be expressed in only one way, as vectors in B. Which is what we had said right at the end of, I do believe it was the last lecture video from the last section, where if we had some equation AX equals B that we were solving, then essentially every solution vector right here, X, could be expressed as only one linear combination of the vectors in the basis, which is where we had finished. Now, we want to kind of expand on that idea a little bit. The coefficients in the linear combination are coordinates of X relative to B. And again, when we say coordinates, we're deliberately using the word coordinates. Now we're going to kind of sort of think about these vectors, at least briefly, as literal vectors that we can graph out, that we have graphed out in R2 or R3, which means we're talking about coordinates, which means order matters. In R2, they're ordered pairs. So order matters here, which means a lot of times we don't call B a basis, we call it an ordered basis, because the order is deliberate. So let B equal a set of vectors V1 to Vn be an ordered basis for a vector space V, and let X be a vector such that X is equal to C1V1 plus C2V2 all the way out to CnVn. The C sub i's are coordinates of X relative to B. And let me just check it. Okay, good. And the coordinate matrix or vector, we understand the words are interchangeable in this case, is X sub B, which is just equal to C sub 1 to C sub n. And admittedly, that's a whole lot of words there. The idea is actually pretty straightforward, which we'll see in a second with a couple of examples. But I have a basis B, I have a vector x, and essentially I want to write x. I know there's only one way to write it as a linear combination of vectors in my basis. So I write out x as that linear combination, and then these coefficients, C1, C2, etc., out to C sub n, form a matrix, or in this case, it'll just be a column vector. So you can say coordinate matrix or coordinate vector, where I just list out those coefficients. The idea being, in R2, I know I have a standard basis 1, 0, 0, 1. Suppose I have some x equal to, we'll say the vector 3, negative 2. There's only one way to write x as a linear combination of those, and it's pretty clear. Again, I know I don't need to do this, but to write it out formally, x is equal to C sub 1, 1, 0, plus C sub 2, 0, 1. And clearly, C sub 1 is 3, C sub 2 is negative 2. Which would then tell me my coordinate vector, or coordinate matrix, x sub b, is equal to 3, negative 2. Which is, again, obvious. From a geometric perspective, I have R2, I have my standard bases. So there's 0, 1, there's 1, 0, and 0, 1. Now I have some vector, I was moving all my markers around using them drawing pictures. Okay, I have some vector 3, negative 2. 3, negative 2, which is right here. And how do I write it in terms of those two bases? Again, I know this is trivial, but I go out to here. I go down to here. I add those two together. If you remember wherever we walked with vectors before, parallelogram law, add these together, you go nose to tail, and you get that. And that's all I'm really doing. Again, stuff we have done before. But to a certain extent then, the question kind of becomes, well, okay, then what if x is equal to 7, negative 2? Well, then my coordinate vector, my coordinate matrix will be 7, negative 2. And again, I'm not really doing anything here. I could make this three-dimensional. I'm not going to try to draw three-dimensional vectors. But, I would just write those three coordinates as a column vector and be done. And the question is, well then great, now I'm really just creating new terminology, coordinate vector relative to a basis, which is really the exact same thing I started with, except that here I wrote it as a vector, here I wrote it as a column vector. But there are other uses for this. I will randomly mention this for the few of you who took trig with me, or if you took it with another instructor, or maybe even in high school. There is one section in your textbook, for the book we use for trig, that occasionally I cover if I have time, but most of the time we don't. But if you were in my class, you may remember me mentioning, hey, this is a really cool thing we can do with vectors, and I think it's really fun, but we're not actually going to do it because we don't have time. And again, if you took trig with somebody else or in high school, it's a cool thing that you can do, but generally speaking, the algebra involved can be convoluted, and due to time restrictions, it never really gets covered. But essentially the idea is, and you will see this in the next section of your book, I do not intend to do a video on the applications in section 4.8. I think you can figure them out. If you don't, I will say it now in this video under the assumption you actually watch these. If there are any applications from 4.8 that you're working through that you have questions about, email me and I'll make a video going through them. But right now my assumption is you should be able to work through those on your own. But one of the things they mentioned in those applications, and actually goes back to trig, when you talk about trig, you say have an ellipse. And if you remember working with ellipses, I hope you do, you're going to use them in the next section. Every single ellipse you do in trigonometry is either horizontal or vertical. You move the center around, make them bigger or smaller, but they're always horizontal or vertical. And the follow-up question is, the kind of natural question is, what if your ellipse is diagonal? And again, I would have mentioned this in my trig class if you had trig with me, which I know some of you did. And I'm assuming if you took it in other classes, your instructor in those classes probably gave you a similar answer. That's really hard to do and it's really messed up. And the algebra takes a long time to do, so we're not going to do it. But in actuality, what you do is, well, you either come up with a really convoluted equation to kind of turn that thing diagonal, or you turn space around the ellipse. Meaning, what if I eliminated my xy axis and instead drew my axis this way? Now that ellipse is horizontal or vertical, to use those words, from the perspective of this axis that I drew. Now the equation is easy to come up with. And now, again, you're really not moving or messing around with the ellipse, you mess around with the space around the ellipse. Then your question becomes, well, okay, how in the world do I take my xy axis and twist my xy axis? How do I twist space? Well, here, I know that 1, 0, 0, 1 actually gives me my xy axis. Again, it's just the unit vectors here, but expand them, and essentially I get my regular xy axis. I know in R2 I can create any basis as long as the vectors that I create are linearly independent. Well, if I could find a way to write this vector and a way to write that vector, those would be linearly independent. They would form a basis for R2. And then maybe instead of using this basis, I could use that basis. And again, this is kind of the idea behind what we're going to do, where essentially I can write everything in R2 in terms of 1, 0, and 0, 1. And this expands to all Rn. But just for R2 for now, I can do everything in terms of 1, 0, and 0, 1. What if I don't want to? What if I want to use a non-standard basis? Is there a way to write a vector using a non-standard basis? Meaning, I have the vector 3, negative 2 right here. But what if I randomly change my basis to say this right here? Then how would I write this vector, which would not change, in terms of the new basis that I created? And that's kind of the goal behind this right here. If you only use your standard basis 1, 0, 0, 1, this is trivial. But if I want to use a different basis, a non-standard basis, then I have to find a way to rewrite everything in terms of my new non-standard basis. That's what we're going to look at. And if I can do that, then essentially I can turn space. I can take these axes and essentially turn them around so that everything is horizontal or vertical relative to the basis that I use. Which is just, again, a useful math thing. And again, there are reasons for it. You don't necessarily go over this in trig. Occasionally we do. I like to go over it because I think it's fun. But now we can kind of set the machinery up to see how that actually works. And if you didn't go over it back in trig, you can go back and do it now. It'll make more sense. So, the good thing is, while that may sound complicated, as I said in the last few videos with all this new terminology and notation, it's actually nothing new. It's all the exact same principle, a lot of Gaussian elimination with vectors and matrices, just new terminology and a new way of looking at it. So let's see. Do an example with a non-standard basis. Say we have this. Suppose my coordinate matrix vector is 5, 1 with the basis 1, 0, 2, 3. Those are not multiples of one another, which means they're linearly independent, which means they form a basis for R2. So that's definitely a non-standard basis. What I want to do is find the coordinate matrix relative to the standard basis. And I'm assuming you can all hear my phone in the background, which I'm going to go turn off now before it hangs up. Okay. Good. So, well, essentially, if I think about the graph over here, that's my standard basis, so I'll draw it this way. Here, I'll draw my non-standard basis. I have to draw it this way in terms of x and y because it's what I'm so used to. But now my basis would be 1, 0, which is right here, and 2, 3, which is right here. So this is my basis right here, as opposed to 1, 0, 0, 1 being my basis here. I'm not even going to bother to try to draw 5, 1 right now, because keep in mind, that would be 5, 1 relative to this, which would mean, I guess, I would go 5 in this direction and 1 in this direction. If I tried to impart some logic here, those of you who know me know I don't think geometrically. 5, 1, this is ordered, which means the 5 goes with this, the 1 goes with that, maybe. So the 5 would go with this horizontal, so to speak. This actually is horizontal. So if that's 1, maybe the 5 goes out to about here. Now I go 1 in this direction, because that's my other one, which would then, if I do nose to tail, put me about here. So I would say my vector looks something like that, up to my ability to reasonably draw this with respect to this basis. Now, if we do this with respect to the regular basis, I should get the exact same vector, but now it'll be written with respect to those. And the question is, how do I do that? Well, let's see. I know if this is the coordinate basis with respect to this, then I write this as a linear combination. So I get 5 times 1, 0, plus 1 times 2, 3, which then gives me 5, 0, plus 2, 3, which gives me 7, 3. Now this is the vector that I want. Now take this vector and write it in terms of my standard basis, 1, 0, 0, 1, which would clearly just be x. Let's see here. If we call that xb, maybe I'll say this is xb prime, would just be 7, 3. with respect to the standard basis. Which again, we can see. This is a little bit hard to do geometrically, again, because I don't think geometrically, but it looks like the vector should be right about here. If I draw that over here, I then convert to the standard basis, 7, 3. Yeah, that looks really reasonable. Which means I can take things using different bases and write them in terms of the standard basis. Or vice versa, if we think about the ellipse, I can take ellipses that are written with the standard basis and write them with respect to a slanted basis. So we can kind of go back and forth here. Do another example to make sure we're kind of following along here. Let's see. Find the coordinate matrix or vector of x equal to 3, 4 in R2 relative to b, which in this case will be 2, 0, 3, negative 1. So now I'm given a vector in R2 relative to a non-standard basis. Now I want to find the coordinate matrix xb, or xb prime. I called that b, so we'll say xb. How do I do that? Well, this may look new, but thankfully I just apply the definition and I use what I already know. By definition, the coordinate x is equal to a linear combination, c sub 1 u sub 1 plus c sub 2 u sub 2. So now I just write it out. X, which is 3, 4, is equal to c sub 1 times u sub 1, this is ordered, so 2, 0, plus c sub 2, x sub 2, 3, negative 1. Now if I, in one step, multiply it out and equate, first coordinate 3 is equal to 2c sub 1 plus 3c sub 2. And then the second coordinate 4 is equal to, that's just 0, plus negative c sub 2. And I get a nice system of equations. All of you can solve these out, so to save a little bit of time, here, if you solve those, c sub 2 is immediate. I get c sub 1 equals 15 over 2, and c sub 2 is equal to negative 4. Which then tells me my coordinate vector x sub b is c sub 1, 15 over 2, negative 4. And again, what that means is, if I drew this vector with a regular basis in R2, 3, 4, if I then drew this coordinate matrix, if I do that basis right there, 2, 0, and 3, negative 1, using those two as a basis, this is what that vector would be written as, 15 over 2, negative 4. But now maybe, well again, now I know that I can take things written with respect to the standard basis and write them in terms of a non-standard basis, or I can take something written with respect to a non-standard basis and write it with respect to the standard basis. I can really go back and forth. We just want to kind of write that out formally to see what's actually going on. So if I maybe write this out using matrices and all that, this right here would be 2, 3, 0, negative 1. And if I then multiplied that by c sub 1, c sub 2, my coefficients, I would get 3, 4, the answer that I wanted. And that's the equation that I was actually solving. And then let's see. We said that this, which was my solutions right here, is my coordinate matrix xb prime. Here I'll just call this prime because I get it in my notes. It doesn't matter. This was where I started, 3, 4, so that's xb. This matrix over here, we're going to call P. It's what's called the transition matrix. Essentially, it's the matrix that transitions from one basis to the other. If I kind of just write this as an equation now, understanding that P is a matrix, I get P dotted with xb prime equals xb. Which means maybe in English, this matrix P takes something written with a non-standard basis B prime and rewrites it in terms of the standard basis B. Which is what this says. Again, here I was actually solving for the C1, C sub 2. But assuming I knew those, multiply P by that, I get 3, 4, which is the vector in the with respect to the regular standard basis in R2. But now, if I can write this equation, I can apply all the algebra that I know. We do not necessarily know, as of right now, that this P has an inverse, but assuming that it does, multiply by P inverse on the left. P inverse times P is the identity, so it goes away. So I'll be left with xb prime equals P inverse xb. And now what does this do? This takes something written in the standard basis and writes it in terms of the non-standard basis. Which means this kind of gives me a nice, simple way to go back and forth between standard basis and non-standard basis. Or by extension, what if I have two non-standard bases? That doesn't really matter. Just call one of them B, the other B prime, and I can go back and forth between them. So let's see. We just want to write this out formally as a theorem. I will point out the proof of this and the lemma in your book. Let's see, we're already half an hour in. Yeah, the proof of this is really not all that challenging. It's just a couple of steps. It just looks really long and cumbersome, so I'm going to skip the proof because I don't want to take an extra 10 minutes just writing it all out. But the proofs are really straightforward. But the theorem. If P is a transition matrix from a basis B prime to a basis B in Rn, then P is invertible and the transition matrix from B to B prime is P inverse. But again, all this is saying is what we can see here. This we did out formally. If we generalize, if I multiply the transition matrix P times the coordinate matrix with respect to B prime, I end up getting the coordinate matrix with respect to B. It goes from B prime to B. But if I multiply by P inverse on the left, I can go backwards. And the transition matrix to go from B to B prime is P inverse. So this is just formalizing what we can already see. The only kind of added caveat is this guarantee of invertibility, which here we were just assuming. Again, the proof actually requires another lemma, which I have written down, but I'm going to decide to skip here, because it's really just a cumbersome lemma that guarantees the invertibility, but it's not that challenging to prove. and then it makes this proof one line and you're done. So in lieu of time and the fact that I don't think any of you want to see it, I'm going to skip it, and we're going to look at how to actually use this, which requires another theorem that we will then apply. Not them, theorem. Let B equal V1 to Vn and B prime equal U1 to UN be two bases for Rn. The transition matrix P inverse from B to B prime can be found by using Gauss-Jordan elimination on the n by 2n matrix B prime B as shown by B prime B to I sub n P inverse. So essentially, if I have two bases, be they one standard, one non-standard, or two non-standard, I can find my transition matrix to go from one to the other by simply writing out B prime B and then doing the elimination and essentially turning the left one to the identity, the right one is the inverse. I will actually point out earlier in the semester when we were looking for inverses, this is actually one of the tricks we used to find inverses. There's multiple ones. This is actually one of them. So we're doing the exact same thing. We're going to do two examples, one with a standard basis, one with a non-standard basis, just so we can see it worked out. But I would also point out, don't get lost in the formality of the way the theorem is written. I can use this to go from B prime to B, but the labeling B prime and B is completely arbitrary, which means I can also find the transition matrix from B to B prime. Just switch those around. Or, just write a prime here and no prime there. Again, it's interchangeable. It doesn't really matter. You just have two bases, whatever they are, standard, non-standard, non-standard, non-standard. And you do the Gauss-Jordan elimination to turn this to this, and that gets you your transition matrix. So, because it's the one we did earlier, let's see. We went from 2, 3, 0, negative 1. That was my P. Let's see. Yep. And now I have 1, 0, 0, 1. And no, this is actually what I did at the end. The basis that I used, I have multiple pages here that I'm pulling up. The basis that I used was 2, 0, 3, negative 1. So this was, we'll say, just to use this notation, B prime. And we'll call this one my standard basis B. Now I want to find the transition matrix to go from B prime to B. So I'm going to do the Gauss-Jordan elimination. I will also point out again, as I find all the correct pages, when we did this, let's see, we got that P was actually equal to the same as that 2301. 230, negative 1. So if I do this right, I should get P inverse here, which would be the other transition matrix, which I'll be able to tell if I multiply these together, they should be inverses. If I do the Gauss-Jordan elimination, here I'm going to shortcut it because we're going to do another example in a minute. And if I do the Gauss-Jordan elimination, I end up getting 1, 0, 0, 1, 1/2, 3/2, 0, -1. This is IN, so according to the theorem, that should be P inverse. And again, we did a version of this earlier in the semester to find our inverse. Write the matrix here, write the identity here, do the operations, this should be our inverse. So I actually did this knowing it's going to work. And if this is my transition matrix, just really quickly, that means P inverse is equal to 1/2, 0, 3/2, -1. 2 times 1/2 is 1, 3 times 0 is 0. That's going to give me a 1. Everything else will work. I'm not worried about it. And again, I stress, this is what we did earlier in the semester to find inverses. So it's nothing new, we're just applying it in a slightly different way. Because converting from a standard basis to a non-standard basis, from the standard to a non-standard, is pretty straightforward. What if we have two non-standard bases? Then it becomes a little bit more complex, but the method still works the same. So that we're going to work through now. So suppose that B is equal to 1, 1 and 3, -2. Not multiples of one another, clearly a basis in R2. B prime is 1, 0, 4, 9. Not multiples of one another, clearly a basis in R2. Now, find the transition from B prime to B. So I write it out. Keep in mind, I write all of these as column vectors. So 1, 0, 4, 9, 1, 1, 3, -2. Now just do all the Gaussian elimination, and this will work through really quickly because you'll notice I set it up. The first one is already done, which means I need to make that a 1. So the first row stays the same. Divide everything by 9 or multiply by 1/9. You get 1/9, -2/9. Now take this row, multiply it by -4 and add it to that. So now the second row will stay the same. 0, 1, 1/9, -2/9. This will still be a 1. -4 times 1 is -4 plus 4, which is 0. -4 times 1/9 is -4/9. 9/9 minus 4/9 is 5/9. -4 times -2/9 is positive 8/9. 3 is 27/9. 27 and 8 is 35/9. Now, this is my identity. This should be P inverse, my transition matrix. If you want to test this to make sure you're doing it right, go back to the beginning and find BB inverse. Do it all out. Then in this case, again, you can call whichever one the inverse you want. Here you would get, say, P as opposed to P inverse. These two things, the results should be inverses of one another, which you can check by multiplying them together. But again, the idea here, and you'll use this a little bit in the next section on applications, given vectors written with respect to different bases, I can now take a vector written with respect to one basis and rewrite it in terms of another basis. And I can go back and forth, which just gives me a lot more fun to play with from a linear algebra perspective, we'll say. Again, I do stress here, this is really nothing new. I mean, like I said, we were using this to get inverses before. The only difference is now, instead of having the guarantee that maybe this was the identity, now it can be something else. Because we understand this is not the only basis in R2, there's a whole lot of them I can come up with. Like I said at some point in this video, I'm not going to make a video going over applications of this stuff from the last section in this chapter. because I've already made like 3 or 4 hours of video this week, and I'm sure you're getting tired of watching them. That being said, if there are any applications, things like the Ronxian and all of that from the last section, if there are any questions, feel free to let me know, and I will gladly make a video going through some of them. But you have to watch this video and hear me say it, and then actually email me and tell me, and then I'll do it.